Hi, and welcome to this video on complex numbers. Now, if you're not interested in complex numbers and don't plan on using them, by all means, go ahead and skip this video. But if you are, here we go. Let's take a look at it. So complex numbers are implemented in Python using the built-in complex class. So it's a class, and so it has a constructor. So the constructor takes two parameters, x and y, and x is the real part and y is the imaginary part. So basically, we're working in rectangular coordinates. Now, of course, you can also have complex literals, and the literals are simply written this way, x plus yj, where x and y are the two numbers, and this j here just represents that is the imaginary part. And j can be uppercase j or lowercase j. Both will work just fine. So just as some examples, we can take a equals complex 1, 2, and b equals 1 plus 2j. Those should be the same numbers, right? They're the same complex numbers. And in fact, when we do a equals b, we get true. But there's a little bit of a caveat to all this. X and y, the real and imaginary parts, are actually floats, right? And actually, even in this case, where we specified x and y to be integers 1 and 2, if you look at the type of them, once they've been created into a complex number, they're floats. And we'll see that in the code. So, of course, being floats, you've got to be careful with the equality testing. Right? We have the same issues here that we have with regular floats. And we'll see that in code, and we'll come back and touch on that later towards the end of the video. So we do have some instance properties and methods. So we have the real instance property, which returns the real part of the complex number. We have the .imag for imaginary, which returns the imaginary part of the number. And we also have a method, conjugate, which returns the complex conjugate of that particular number. So just as an example, if we take d equals 2 minus 3j, then d.real will return 2, d.imaginary will return negative 3, and in fact, those will be floats, right? So, and we'll see that in the code, but just keep that in mind. And then d.conjugate will return the complex conjugate, so it will return 2 plus 3j. The arithmetic operators like plus, minus, division, multiplication, and as well as powers work just as expected with complex numbers. So they work just fine. They're polymorphic. They're recognized when they're working with complex numbers. So you can add, multiply, and do all those things with complex numbers without any problems. Here are some examples. You can also mix real and complex numbers. So if you want to add a complex number to a real number, that's fine. Obviously, in real life, in real mathematics, that works just fine. Here as well, that is supported, as well as multiplication and the other ones as well. So nothing fancy here. They work as expected with complex numbers. They just use complex arithmetic. Now, the div and mod operators are not supported, right? So if you try and do a div and mod operation on complex numbers, you will get an exception. Now, other operations. Let's talk about the equals and the not equals. So they are supported, but again, we have the same problem as with floats, right? Complex numbers are stored as floats, which means that the equals is going to raise problems because we're not going to have exact representations of the numbers that we put in as maybe, as finite decimal representations. So we'll run into the same problems we had with the floats. Now, the comparison operators such as less than, greater than, again, also are not supported, right? I mean, what does it mean for a complex number to be greater than another one? Well, it might depend on your definition. It might depend on what, you decide to be that ordering of complex numbers. So in general, they're not supported. You'll have to, create your own, basically. Now, functions in the math module will not work. You cannot use any of the functions in the math module with complex numbers. Instead, you should use the CMath module, which is basically the complex equivalent to the math module, and it has most of the same functions in there, plus some extra ones that are more specific to complex numbers. So you have exponentials, you have logs, you have trigs and inverse trigs, you have hyperbolics, inverse hyperbolics, you have polar and rectangular conversions. That's an example of some of the functions that are in the CMath module that are not in the math module. And you have also the isClose method, which is also in the math module. And this one is, will work with complex numbers, but it does the same thing. So if you need a refresher on the isClose method with floats, you can go back to one of the videos on floats where we discussed that in some detail. But it works the same way. All right, so first, let's take a look at rectangular to polar. So just a quick recap, reminder of the notation as well. So we have the real and imaginary axis. We've got this complex number here, x, in rectangular coordinates. And it also has polar coordinates, right? This angle phi and r. So if we import the CMath library, then we can use the phase function in there, which will return phi, right? It will return the phase or the argument of the complex number x. Phi will be between negative pi and pi, right? And it's measured clockwise from the real axis this way. So you go from, you will go from negative pi to pi, right? You're measuring clockwise from the real axis. If it's down here, then you're going to be measuring clockwise from the real axis, which means you'll get a negative number. And that's why you get negative pi to pi. But that's pretty standard. That's how it's done usually for complex numbers. Now, the r value can be obtained by using the absolute value function. So we can use abs.x, and that will return the magnitude, essentially, of this vector, if we think of this as a vector. And it's just the Euclidean distance. It's just going to be r. So it returns the magnitude. So, for example, a equals -1 plus 0j. Then we can say CMath.phase of a, which will return pi, and r will be 1, right? -1 plus 0j is sitting out here somewhere at a distance of 1 from the origin. So the angle is pi, which is what we get, and r would be 1. On the other hand, if we take a equals -1j, well, it's sitting down here, right? So we get an angle of -pi/2, and we get an r of 1 as well. And then if we take x to be 1 plus 1j, so sitting out here at an angle of 45 with coordinates 1 and 1 basically on this chart, then our angle is pi/4, right, 45 degrees, and the absolute value of a, this Euclidean distance, is square root of 2. But of course, we'll get 1.414. We won't get an exact representation since square root of 2 is irrational. All right, and then we have the reverse. We can go from polar to rectangular. So again, we use the CMath library, the CMath module, and we can use the rect function, which takes in the r and phi, the polar coordinates of the complex number, right? And that will then return a complex number, which will be in rectangular coordinates. So for example, if we take what we had in the last slide, right, where we take r to be the square root of 2 and phi to be pi/4, right? And you'll notice here that I used math.pi/4 and math.square root of 2. I'm not taking the complex square root of 2, I'm just taking the real. So I'm using the math module. And with pi, it doesn't matter. I could have used cmath.pi or math.pi. It's the same number, right? And we'll see that in the code where I'll mix sometimes the pi, right? But this one, you've got to be careful. You can't use cmath.square root of 2 because cmath.square root of 2 will actually return 2 plus 0j. It will return a complex data type. And this rect here expects a non-complex data type in the first parameter, in the first argument. So be careful there. So that should return 1 plus 1j. And it does, right? But again, we're using floats. We have irrational numbers. We have this irrational transcendental number here. So it's not going to be exact, right? And even with finite representable decimal numbers, you might not get a finite representable binary float, like 0.1, as we've seen before. So lastly, let's take a look at Euler's identity. It's one of my favorite equations, not just in complex analysis, but in math in general. I just think it's an awesome equation. And let's test it out. Let's make sure that we actually get that in our code. So we would do it this way, right? We would do cmath.exp, which is the exponentiation function in the CMath module. And we're going to take I pi. So we need to take pi times I. So we're going to do it this way. We're going to take cmath.pi. I could have used math.pi, doesn't matter, times 1j, right? Which is basically 0 plus 1j. So we're multiplying pi times I. When you think of I as the imaginary, that's kind of the more typical notation. And then plus 1. And that should give us 0, but it doesn't. So it kind of spoils the effect, right? So these floats here kind of spoil the effect, plus the fact that, we have to represent pi we have to do it using a finite representation, and so we end up with something that's close to 0 but not exactly 0. So the next best thing we can do is to use the isClose method, and it works the same way as with floats. So we're going to say cmath.isClose, cmath.exp, cmath.py, this is the same expression we had up here, and we're going to test to see if it's close to 0, and we are going to specify an absolute tolerance. We have to, right? Because we're testing numbers that are very close to 0. This one is close to 0, and this one is actually equal to 0. So in this case, the relative tolerance is not going to work. And again, if you need a refresher on that, you can go back to the video on floats where we discussed the isClose method there and some of the caveats that you have to watch out for. So we have to specify an absolute tolerance, and then when we do that, we get that this result is true. So indeed, we find that, e plus I pi plus 1 is equal to 0, right? It's close enough to 0 to be considered true. Now again, as I just mentioned, if you don't specify the absolute tolerance, so if you just run the method this way and settle for the default tolerance, which is a relative tolerance and an absolute tolerance of 0, then you will get that this is false, right? So be careful. You should really specify the absolute tolerance, just as with floats. All right, so now we can switch to some code and take a look at all of that. Thanks for watching, and I'll see you in a bit.